Again, I think I emphasized before, colligative properties depend on numbers of particles in the solution, not what type. So we deal with electrolyte solutions, right? Things like sodium chloride or sodium sulfide. When they break apart, they have multiple particles. So 1 mole of sodium chloride gives you 2 moles of particles. This is why you throw salt on your sidewalk and not sugar. Sugar doesn't break up into multiple particles, whereas something like calcium chloride does. Several important properties of solutions depend on number of solute particles in the solution, not the nature of the particles. So you get a compound that gives you multiple particles, you're getting a greater colligative effect. So when you're dealing with boiling point elevation, if you're dealing with something like sodium chloride, you get what's called a Van Hoff factor, a number that you're going to multiply the molality by to indicate actual number of particles. So I would stand for 2 if you were talking about sodium chloride. You're getting twice the colligative effect with a certain molal solution of sodium chloride. Twice the colligative effect in terms of freezing point depression with something like sodium chloride. So a Van Hoff factor is how many multiple of particles you get when the substance dissolves in the water. All right, so there's a discrepancy between, all right, like I just boldly said, right? You get something like calcium chloride, right? CaCl2. For every 1 mole of calcium chloride, you're getting 3 moles of particles. Well, there's the calculated value, right? What it's supposed to do, and then there's the measured value. So for something like hydrochloric acid, where I've got 2 particles breaking up every time hydrochloric acid goes into solution, I'm not quite getting a 2-fold effect with hydrochloric acid like it had a 2-particle effect. I'm getting a little bit less. All right, 1.9, so let's not quibble. That's almost 2. Something like sodium chloride, right? When you put it in water, you expect a Van Hoff factor of 2, twice the colligative effect. Again, it's 1.9. It's not quite 2, but close. With something like magnesium sulfate, though, right? I mean, magnesium sulfate breaks up into 2 particles, right? Magnesium ions and sulfate ions, 2 times the colligative effect. Well, when you actually look at the measured value, it's only 1.3. It's closer to having a single particle effect as opposed to a 2-particle effect. Magnesium chloride, you're expecting a Van Hoff factor of 3, right? 3 moles of particles for every 1 mole of magnesium chloride. You're getting less. It's 2.7. Iron 3 chloride, you expect a Van Hoff factor of 4, and you're only getting a measured value of 3.4, much less than a 4-fold effect. So why? Why the discrepancy between the measured effect on colligative properties and what you're calculating? The theory is what they call ion pairing, that these ions aren't truly separating enough to be considered separate particles. So when you have something like magnesium sulfate, right, the magnesium ion and the chloride ion are kind of finding each other and staying stuck together as a single particle. So when a mole of magnesium chloride, which is soluble, right, breaks apart, it's not quite breaking apart into magnesium ions and chloride ions. It's breaking into these magnesium chloride units that are floating around, acting like single particles. So an ion pair, right? All of a sudden, these 2 things are close together, and it's acting as like a single particle as opposed to 2 separate particles. What is the freezing point of a solution where you've got 250 grams of calcium chloride, a strong electrolyte, soluble ionic compound, in 1 kilogram of water with a Kf value of 1.86 degrees Celsius kilogram per mole? Well, we can't know what the adjusted value is for calcium chloride. All we can know is what the actual Van Hoff factor is. So for every 1 mole of calcium chloride, you're getting a 3-fold effect in terms of the ions. Right, so the first thing we need is molality, right? Use the molar mass of calcium chloride to convert to moles. Divide by kilograms of water. and I get the molality of the solution. I'd multiply that by the Kf value, taking into consideration that with an electrolyte solution, you got a Van Hoff factor of 3 here. So I multiply the whole thing by 3. K times M times 3 gives me a calculated effect of 12.5 degrees Celsius. So water usually freezes at 0 degrees Celsius. So if you use calcium chloride on your sidewalk, which is what road salt is, you're getting a threefold colligative effect, or at least a calculated threefold effect, and water freezes at a much lower temperature now, right? Minus 12.5 degrees Celsius as opposed to 0. So that's how you deal with Van Hoff factors. All right, there are solutions that aren't really solutions. For example, milk. Milk, you've got these large particles floating around in the water that make it look milky, and they never settle out. But it's not technically considered a solution. These are floating particles that are too large to be considered ions or molecules, so they're considered colloids. Some colloids have a hydrophilic end, some have a hydrophobic end, and this is how soap works, right? So when you put certain molecules into the water, some part of the molecule is going to be attracted to the water, the other particle is going to be repelled by the water. So this is how soap works. Soap surrounds an oil particle on your hand with the hydrophobic end, right? So the hydrophobic end is attracted to the oil on your hand, whereas the hydrophilic end of soap is attracted to the water. So you get these little bubbles surrounding the oil that's on your hand, and they get sloughed off by the fact that there's a hydrophilic end to the soap particle that's attracted to the water. So soap, hydrophilic end, part that's attracted to the water, polar, and a non-polar end that's attracted to the oil that's on your hand.